Up to this point in factoring quadratics, we've developed two methods to use. First one being GCF, and second one being a equals 1. So if I'm presented with this problem, and I look to do this in the order of GCF and then a equals 1, I check out the coefficients first to see if there's any number I can pull out from a 2, a -5, and a -12, and there's not. I check out the exponents and the x's. There's nothing I can pull out, so GCF in this case is useless. So then I go to a equals 1, and I notice very quickly that my a value is a 2, so that method is also very useless. So we're going to have to expand our tools and introduce another method of factoring called a is not 1. A is not 1, again, is used to factor quadratic trinomials of the form ax squared plus bx plus c. And since there's more than just a equals 1 in terms of problems that we can do with this, the process is going to be a little bit more complicated. So let's look at the process as we look at an example. The example is going to be the one we looked at before, 2x squared minus 5x minus 12. And my first step is now going to be find factors of AC, a times c. So I look at the leading coefficient and the constant, multiply them together, that add to b, where b is still the coefficient on the linear term. So if I apply that process to my original example, I have a 2 as my a and a -12 as my c. So the AC value is -24, and the b value is going to be -5. So I go through and list out everything that multiplies to give me 24. Remember, I'm not really concerned about the negative yet. So I have 24 and 1. I have 12 and 2. I have 8 and 3. And I have 6 and 4. Those are my options. And I look at who can I add or subtract in order to get a 5. And later I'll worry about the negative. So I can't do that with a 24 and 1. Can't do that with a 12 and 2. Or a 6 and 4. So I'm left with 8 and 3. And in order to get a negative with the 5, the bigger number, or the 8, has to be negative. So those are my two numbers right there, -8 and 3. And now I need to go through and do a little bit more with them than I did with a equals 1. With a equals 1, I could hop right to my answer. But now I have to take those two numbers and use them to replace the middle term. And by middle term, I'm referring to the bx term. So I come up here and I leave the 2x squared the same. But I'm going to go ahead and split up -5x into two pieces. I'm going to make it -8x plus 3x and keep the -12. And I haven't changed my problem at all because -8x plus 3x is still -5x. I've just changed the way it looks. So replace the middle term. And then my last step is to split the problem. So take it in half, right down the middle, and use GCF. I'm going to use GCF to complete this, but I'm going to have to use GCF twice. So let's see what that looks like. If I take the GCF of just the first two pieces, I end up getting a 2 that I can pull out from both, and an x. And I'm left with x minus 4. That's from the first half. Take the GCF out of the second set, I get a positive 3 that I pull out, and they don't share any x's, so I'm left with x minus 4, because I divide the 12 by the 3. And what's wonderful here is that if I continue to look at this as a problem with two pieces, and I think back to GCF and realize if they have the same binomial, I can go ahead and just yank that out front. So I'm allowed to take that x minus 4 and factor him out, and then just look at what are all the pieces that I have left once I factor him out, because he's gone, taking him away and taking him away. And I'm left with a 2x plus 3. And in that case, I have my fully factored form using a is not equal to 1. It's easy to see that I couldn't just use the a equals 1 process because I end up with a coefficient on one of my x values, or at least one of my x values. It could be both. So if I were to FOIL this out, I would get right back up here where I started, because remember, FOIL and distribution are inverses. So these are my 3 steps over here on this side as to how I use a is not equal to 1. It's really just a lot of GCF after I split the problem in half. So let's look at a second example. For the second one, I want to start out again with a quadratic trinomial. It's going to be 3x squared plus 10x plus 7. And I go through my list of possibilities. Can I use GCF? No. Can I use a equals 1? No. So I have to use a is not equal to 1, where I look for factors of AC that add up to b. In this case, a is 3, b is 10, c is 7. So factors of 21 that add up to 10. So if I make my list, 21 and 1, 7 and 3, I quickly realize my 2 numbers are going to be 7 and 3. So I split the middle term in half. I exchange the 10x for a plus 7x and a plus 3x, and keep the quadratic term and the constant the same. I didn't change the problem, I just changed the way the problem looks. So split them in half and look for GCF out of each of these pieces. So in the first piece, I can go ahead and pull out just an x because they don't share anything else in common. And I'm left with 3x plus 7. And I look at the second piece, and it doesn't look like there's anything I can pull out. But in order to factor GCF in the next step, I have to pull something out from both of those. So if I can pull nothing else out, I get a 1, and that leaves me with 3x plus 7. The key is I have to get these 2 binomials to be exactly the same if I want to factor them out using GCF in the next step. So I have to factor something out. In this case, I factored out a 1. So to finish this problem, again, I think of it as being split in half, factor out the common piece, which is 3x plus 7, and then everything that's left over is the x plus 1, and that becomes my second binomial. So my final answer is 3x plus 7 times x plus 1. And again, if I were to FOIL it out, it would take me right back up there and complete my cycle. Lastly, a third example, if I start out with 4x squared minus 49. This may not look like a quadratic trinomial of the form ax squared plus bx plus c, but again, I can make it that form if I reintroduce the bx term. So I write it out so it's easier to see as 4x squared plus 0x minus 49. This allows me to find the AC and the b, AC being negative 196 and b being 0. So I want to look for numbers that multiply to negative 196 and add to 0. I know it has to be the same number, positive and negative, so I can take the square root of positive 196 and realize my 2 numbers are 14s, and one of them has to be negative. It's a little quicker than going through all of the different options. So I split the middle term, split the 0x term up, which leaves me with 4x squared as the first part, plus 14x, minus 14x, minus 49. Again, I split him into those 2 different pieces. Didn't change my problem, just changed how it looks. So go through, cut the problem in half, and look at GCF on each piece. In the first piece, I can easily pull out a 2, and I can pull out an x, which leaves me with 2x plus 7. I really want to get a 2x plus 7 out of the next term, positive 2x and a positive 7. So I look at it and think, well, out of a 14 and a 49, I can pull out a 7, but I also want to make sure that they're positive. So if I pull out a negative 7, that leaves me with a positive 2x when I divide, and a positive 7, which is exactly what I want, because now I have these 2 binomials, which are the same. That allows me to continue on with GCF and just yank those out. So I pull the 2x plus 7 out front, and I'm left with 2x minus 7 as my second binomial. And if you notice, these are conjugates, so it makes sense that the middle term is going to cancel out when I FOIL out, which would give me 4x squared minus 49. So A is not 1 is a more complicated process, a little tougher, but if you can get down GCF and just use that repeatedly, you're going to find that it's not that difficult.